All right, AP Environmental Science. Today, we're going to continue with our discussion on Unit 6, which is on energy. And today, we're going to start focusing a little bit more on fossil fuels. We talked yesterday about non renewable energy, and we talked about different resources that we can use to obtain energy and how those resources are used. We talked about a lot of data, global data, and also United States specific data. But today I want to talk specifically about one way that we use energy, not just in the United States, but around the world. In the United States, 40% of all of our energy consumption is just used to generate electricity. So this is kind of like a big part of our daily lives. I want us to think yesterday, I showed you a bar graph that showed you different countries around the world and how much energy those countries use. And we talked about two countries, China and the U.S., as being two of the main culprits when it comes to energy usage around the world. We said that 40% of all the energy use in the world is from two countries. Now, a lot of that energy is due to the generation of electricity. So we're going to talk about this process today, and why it's such a need for us. You can probably imagine why we need electricity. Right? It's a really important part of our lives. But you got to remember, there's a lot of countries around the world that don't nearly use as much electricity as what we do here in the United States per person. So that's something to kind of remember. Now, when we generate electricity, it comes from something. It's like when you charge your cell phone, it's not like there's an electricity tree, that we can just plug into and get electricity. Like, I mean, it has to be made, it has to be generated from something. Now, typically, there are four different ways or four different sources in which we can get electricity from. Now, in the United States and pretty much globally, fossil fuels, specifically coal, is the biggest source that we use to get our electricity from. Another way is water. It's called hydroelectric electricity or hydroelectric power. We'll talk about that more next week. Wind energy, we can get electricity from wind, like windmills. And finally, nuclear. We can generate it from nuclear fuels. And these last three here, again, we'll talk more about these next week. But today, I want to really focus on the big one, which is generating electricity from coal. So before we get into the process, there's a term here called an energy carrier. An energy carrier says here it's something that can move and deliver energy in a convenient, usable form to users. So, I mean, electricity is a good example of an energy carrier, right? It carries energy into our homes, and we can use that energy for a variety of things. So, just make sure we know what that term energy carrier refers to. But electricity is an example of that. All right, now, um, when it comes to coal, I mean, because coal is a fossil fuel, um, we, we have to burn it. In fact, on the next slide, I'm going to show you how electricity is generated from coal. But um, I don't care what the fossil fuel is. I don't care if it's coal or if it's oil or gasoline you put in your car or the natural gas that your stove runs off of in your house. All fossil fuels contain something called hydrocarbons. Now, you might remember hydrocarbons from chemistry class. Hopefully, you do. But a hydrocarbon is basically just a compound that has just carbon and hydrogen in it. All right, like for example, a good example of a hydrocarbon is methane. Methane has the formula C8. I'm sorry, whoops, sorry, that's not it. Let's cross that off. Methane has the formula CH4. Okay, CH4 is about as simple of a hydrocarbon that you can get. It only consists of one carbon atom. and it consists of 4 hydrogen atoms. But that's what a hydrocarbon is. I mean, there's other hydrocarbons. You probably heard of things like octane, maybe propane. Those are all other examples of hydrocarbons, but they just contain carbon and hydrogen. Really, the only difference between them is how many carbons and hydrogens they have. But regardless, anytime you burn a fossil fuel, you're gonna be burning these hydrocarbons. Now, the word combustion is just a fancy word for burning. So when something burns, it reacts with oxygen. That's what's happening here. So when let's for example, light coal on fire, right? I mean, that's what we're doing. We're burning the coal. We're taking the hydrocarbons that are in that coal and we're reacting them with the oxygen gas that's in the air. That's what happens during combustion. Now, the thing about combustion is it does produce a tremendous amount of heat. And it kind of depends on what the source is as to how much heat you get. But just coal in general, you burn it, tremendous amounts of heat and energy are produced from that, which makes it a good fuel, right? The more energy you get, the better fuel it's going to be. But the thing is, there's also 2 other products that are produced. One of them is water in the form of steam, okay, because this is a burning process, so this isn't liquid water, this is gaseous water that gets produced. And the other product is one that you're probably aware of, is carbon dioxide. Now, carbon dioxide, is a greenhouse gas. And every time, for example, like whenever we exhale, right, we breathe out carbon dioxide. So you're probably like, well, how bad can carbon dioxide be? Well, I mean, carbon dioxide is always going to be in the atmosphere no matter what. It is a greenhouse gas. It does keep our planet warm. But the thing is, we're burning so many fossil fuels that we're putting so much more carbon dioxide into the atmosphere on top of all the CO2 that animals respirate. So, I mean, it's just building up and building up and building up in the atmosphere, and it's becoming very problematic because, again, carbon dioxide contributes to global warming. So, this combustion reaction, the more people we have on this planet, the more fossil fuels we burn, the more of that carbon dioxide is going to get into the air. You do need to be familiar with this reaction. Okay, this reaction again, hydrocarbons plus oxygen, that's combustion. And what does that produce? All right, CO2 is the real bad guy here. Okay, that's not a good thing to be putting up in our atmosphere in great abundance. So remember that. So let's take a look here at the process of how we generate electricity from coal. All right, so I'm going to kind of walk you through this process here, and it's going to be up to you to understand some of the terminology, and again, just kind of some of the general um, um, activities that involve a coal-fired power plant. So we're going to start over here on the left. We're going to start with our coal. Now, the one thing you have to understand about the coal that's used in a power plant is this coal here that's in this whatever tower or whatever this is. Um, that coal has already been mined and it's already been refined. So before it even gets to the power plant, there's been a lot of environmental damage done already. The earth has been disrupted, all the overburden has been removed just to access the coal. During the refining process, lots of pollutants are produced during that process, and then we get the coal. Then we're ready to burn it. So I do want you to understand that there is a tremendous amount of pollution prior to it even getting here. All right, now, if you just kind of take a look at the picture and kind of follow along with my little cursor here, you'll notice that there's like this little chute, this little slide that kind of slides the coal into this big device here, which is called a pulverizer. You can probably imagine what goes on inside the pulverizer, right? It just crushes up the rock into smaller and smaller particles. And basically, by the time the pulverizer is done, you've got a very fine powder of coal. It's very fine at this point. So again, we just kind of mechanically or physically kind of crush that coal into much smaller particles. Now, from there, it enters something called the boiler. Now, the boiler, you can probably imagine what happens here. This is where the combustion takes place. So you'll notice here that there's a little flame here, right? So all of that pulverized coal comes into the boiler, and that's where it's heated. Now, you'll also notice that coming into the boiler as well is a pipe, and this pipe is carrying water. In fact, if we trace this water all the way back, that water has to come from somewhere, right? I mean, it could come from a lake or a pond or a river. It could come from maybe a holding tank. Maybe there's a water tower nearby where it holds the water. But that water comes from somewhere. All right. So that water is, again, that's fresh water, by the way. So that water kind of gets pumped in, right? That water's fairly cool. But once it gets to the boiler, all the heat that's generated boils that water. That's why we call it a boiler, because it boils the water. And it produces steam, it produces gaseous water. So all of that steam travels through this pipe and it travels down in this direction, and it's used to spin something called a turbine. Now, a turbine, think of it as kind of like the crank on a pencil sharpener. If that crank is turning, then the pencil sharpener is doing its job. If the crank isn't turning, then the pencil sharpener doesn't work. Well, the turbine, when it spins, it's used to it's used to operate the generator. The generator is what produces the electricity. If the turbine stops, the generator is not going to be producing electricity. So there has to be a constant flow of steam that comes into this turbine in order to spin it, in order to eventually get electricity. So I want you to think about that. I mean, in order for this turbine to spin, that water has to constantly be boiled, which means there has to be a constant flow of coal that comes into this boiler so that it can be heated. Now, once that steam spins the turbine, you'll notice that there's something called a condenser right below it. A condenser does exactly what it says it does. It cools or condenses all of that gaseous steam, and it cools it off to water again. So this water that leaves the turbine, that water is a little bit warmer than what it was when it came in. That water is going to be exiting. So I want you to think about these two pipes here, this blue one and this red one. When the water flows in to the power plant, it's cold. When it flows out, it's hot. So, I mean, think there's a lake or a pond or a river where this water's coming out of. The water being pulled out is cold, and when it goes back in, it's hot. So think about the organisms that might live in that lake or live in that pond or live in that river. I mean, you're changing the temperature of that's called thermal pollution. When we alter the temperature of a body of water, we're altering the environment for those living things. So that's a big problem as well. So nobody really thinks about that problem, but it is an issue. So again, once the generator produces its electricity, then it can be transmitted to wherever it needs to go. Now, in some cases, it goes directly to your home. In some cases, it goes to another power plant. It can be distributed in different directions. But all that electricity eventually is going to go somewhere. Okay, so this is kind of a big diagram. It's important that we understand how the electricity is produced. So I want you guys to kind of understand this kind of general direction here of the energy flow. All right. Um, this picture here, which we kind of looked at yesterday, what I just explained on the previous slide is basically, oops, I do my cursor there, there it is basically all of this here. This is what I kind of just explained to you. Okay. So like when all of that coal comes into the power plant, it's ready to be burned. So think about what had to happen to all of that coal before it even gets there, right? It had to be extracted, it had to be mined, it had to be transported, it had to be processed or refined, and then it's ready to be burned. So again, there's a lot of stuff happening prior to it even getting to the power plant, and then of course all this stuff occurs. Now, there's one more big thing I just want to I kind of want to mention this because I do think it's important. I'm going to go back to the boiler. You know, whenever that coal is burned, um, it's going to produce waste, and that waste is in the form of ash. So all of that burned coal eventually turns into ash, which is basically just useless. It doesn't really serve any purpose. It's loaded with pollutants as well, and it has to be carried and disposed. So, I mean, we have to get rid of all of that waste. We call that slag, and it has to be disposed of. We'll talk more about that when we get into our units on like air pollution and water pollution. But it's a big deal, like getting rid of all of that waste. So that's not good. So there's two big problems here with this process. One is there's a tremendous amount of pollution that's created, a tremendous amount that we have to deal with. The other big thing is that we talked about this yesterday a little bit, is that the whole process is only about 35% efficient. Once that electricity gets to your home, again, most of the energy has been lost as heat. Only about 35% of the energy even gets to our home. So this is not a very efficient process by any means. Now, one of the ways that we actually can sort of combat that problem of inefficiency. This is called cogeneration. So I want us to kind of think about what we talked about on that previous slide with the power plant. For example, here's your fuel, here's your coal, right? And we burn that coal, and eventually that will end up spinning the turbine and operating the generator, and that's how we get our electricity, right? And that electricity can go into your homes or into a school building or wherever, right? So this process here kind of vaguely is how electricity is generated. Now, the thing is, when we generate that electricity, there is a tremendous amount of heat that gets produced. In fact, I'm going to go back to this real quick. A lot of that heat in the boiler, yeah, it's used to boil the water, but you'll notice that there's this huge smokestack here. All right, and that smokestack is releasing all of the exhaust gases, including carbon dioxide, which is a big problem. But it also produces, excess water vapor and steam, and all these things are produced as well. So if those things are all just given off into the environment, then we lose them, completely. But what one of the things that we've been able to do with technology is we've been able to recover a lot of that heat, a lot of that steam, and a lot of that hot air, and we can use that to actually heat a school building or your home or whatever. We call this cogeneration. So instead of letting all that heat escape, we can use that heat for a useful thing. All right. And if we did this, it would make it a lot more efficient. Now, the problem with this is, even though like a lot of newer technologies, like for example, like brand new school buildings or a lot of brand new commercial buildings, whatever, they may operate using cogeneration, so they can generate the electricity and they can also utilize the heat to help heat the building. But this is a fairly new technology, and a lot of older buildings don't have this. So if they were to convert to cogeneration, it would probably be really expensive, and it is really expensive. So that's kind of the drawback of it. But I mean, this does help with the inefficiency problem of losing so much heat, during the process. It does make it a little bit more efficient of a process. So that's what cogeneration is. All right, so a couple terms here I do want you to know. The word turbine. Make sure we know what a turbine is. That's used to operate the generator. Another term is called the electrical grid. The grid is basically all the transmission lines, and these transmission lines basically carry the electricity from point A to point B. So they can be used to link several power plants together. You might have two or three power plants in an area that can all flow, into these transmission lines, and from there they can distribute all the electricity to your home. So make sure we know what the electrical grid is. All right, a couple more things here real quick. The term capacity. Capacity is basically how much energy can the power plant produce. There's a term here called, or a unit here called a watt, that I want you to know. It's a unit of electrical power. 1 megawatt is equal to 1,000,000 watts. So if you ever hear the term megawatt, we know what that is. But a watt is a really tiny unit. Um, a typical power plant, this is your average power plant, at any one time can produce about 500 megawatts. So, for example, the power plant that we get our energy from, probably is producing about 500 megawatts uh, at any point, at any time during the day. Now, since there's 24 hours in a day, we can take that 500 megawatts, we can multiply it by 24 hours, and we can get this unit here called a megawatt hour. So, in a typical day, a typical power plant can produce about 12,000 megawatt hours worth of power that a multitude of homes and businesses can use. Think of this as like, a lake. It's a lake of power, a lake of energy. And you could have multiple people taking fish out of that lake, right? Think of this as like a commons. Well, I mean, if too many people draw from this, then that might be an issue. Okay, but if everybody kind of uses it sparingly, then we can kind of share this resource and we can use it for electricity in our home. I don't know if that's the best example of that or not, but I mean, we basically all share this energy. Okay, a megawatt hour, this unit here, is equivalent to 1,000 kilowatt hours. Now, the thing about the unit kilowatt hour is this is pretty much how your electric companies are going to charge you or charge your parents to use electricity. For example, every one of your homes, when they pull electricity, from that power plant, they're typically pulling out a certain amount of kilowatt hours every single month. For example, when you turn on a light bulb, that light bulb is pulling electricity from this lake, right? The analogy that I used before. So every single month, for example, the electric company basically measures how many kilowatt hours your home uses. And they charge you for that. And it's usually about 10 cents per kilowatt hour. For example, this is kind of how they calculate your energy bill in your house. So in your home, you have an electrical meter. You may or may not know where it is, but you probably have one somewhere in your house. Everybody does. And at the beginning of the month, let's say that this is what your meter reads, 40,803. That number is kilowatt hours. Okay, that's where you start with. I apologize. This is what your current meter is. So this number below it is what your meter read a month ago. So the difference in those two numbers is how many kilowatt hours your house used or your family used in your house for that particular month. So what they'll do is they'll take those kilowatt hours and they'll charge you a certain amount, in this case, 0.095 cents, per kilowatt hour, about 9.5 cents, about what that is. And then they just figure out what your bill is. In this case, it's $95. Of course, they always add some type of a monthly fee, processing fees, or whatever they do to that. And that's where that $10 comes from. That's where they kind of tack on a little bit of extra. But in this case, your bill ends up being $105. So it really is pretty simple. They measure your meter. At the beginning of the month, they measure it at the end of the month, figure out how many kilowatt hours you use, and they charge. This is why your parents are probably always telling you to turn the lights off and all that type of stuff, because if you leave the lights on, you're using more kilowatt hours. So this is one thing that you can do in your home to conserve energy, is, just like turn the lights off when you leave your bedroom or something like that. So something that's this is a kind of an old school electric meter. Most of the ones now are digital, but I still think it's kind of important to be able to read an electric meter. So whenever we read these, we always start from the right. See where it says start here. So kind of look at this as kind of like a clock a little bit, okay, even though it doesn't go up to 12, it goes up to 10. So if you start here, we're just going to move in kind of a clockwise fashion. And when you get, for example, if you look at the little dial here, you'll notice how it goes past 6. So that means the first number here is a 6. So we go to the next dial, we're going to be moving to the left. You'll notice this one here, the numbers are opposite. So we're going to go in the opposite direction. We're going to go in the counterclockwise direction. So in this case, if we're going counterclockwise, we go past the 5. So that number is a 5. And then you go to the next dial, we're going to go in the clockwise fashion. We go past the 2, that's a 2, et cetera, et cetera. So let's say this is what your electric meter reads right now, 73,256. Well, if that's what it reads right now, whatever it read 1 month ago, the difference is going to be how much energy you use or how many kilowatt hours you used for that particular month. It used to be where they would have a kind of a meter guy or a meter reader would come to your house and they would write down what your meter read. Nowadays it's all done electrical, it's all digital now, so they don't really do that anymore. But maybe in some places they still do. I don't know, but just make sure we kind of know how to read one of these things. It's really not that difficult. All right, last thing here, just a little sample problem that I want you to be able to do. It says here a watt is a unit that measures the rate of energy use. And it says here 1,000 watts equals 1 kilowatt. All right, kilo is 1,000, right? A kilometer is 1,000 meters. A kiloliter is 1,000 liters. A kilowatt is 1,000 watts. So it says here the total energy used over a given period of time can be calculated by taking kilowatts and multiplying it by hours. And we get what we call kilowatt hours. So it says here if an electrical appliance, let's say, for example, a lamp in your home or something, it says it uses 500 watts to operate for 6 hours. If we want to figure out the total amount of energy used, all we have to do is convert watts to kilowatts. So basically just divide it by 1,000. That's where this 0.5 came from. And then just multiply it by how many hours you use that appliance. And then you get 3 kilowatt hours. So let's say, for example, this particular lamp, let's say you had it turned on for 6 hours that day. It used 0.5 kilowatts for 6 hours. That means the total amount of energy that was used was 3 kilowatt hours. So if your electric company, let's say, charges you 10 cents per kilowatt hour, then that lamp, it costs you 30 cents to run it for 6 hours. That's what that is telling us. So I want us to be able to do some simple, calculations using electricity. I don't think this one is too difficult, but we should be able to handle this type of problem. All right, guys, that's it for today. Have a good day. I will see you soon.